Right. So next, I'm going to talk about the BRAT model, which I already talked about when we were dealing with the network models, and that was this beaver restoration assessment tool. And if you recall, that was a network model. So instead of like the fuzzy model we just went through, which is applied on a cell-by-cell basis, say in a raster, this is a model that's applied on a segment-by-segment basis across a drainage network. And instead of predicting habitat quality or habitat suitability or for fish, this is just predicting the upper limit, the maximum number of beaver dams that we could support in that stream segment, so dams per kilometer. And this is some work that Wally McFarlane, Martha Jensen, and Jordan have been instrumental in working on. Excuse me. So as I mentioned in the network lecture, the way BRAT works in a nutshell is well, it actually combines a capacity model with a conflict model. And looks at capacity in the current day in contrast to estimates of what capacities were historically, and it uses those three lines of evidence to then come up with recommendations for how beaver might be managed. And so it highlights areas in the network that are unsuitable for beaver dam building activity, whether that's a natural limitation and they've never been suitable or an anthropogenic. Then it also looks at areas that might be suitable as restoration or conservation zones using beaver as a restoration tool versus areas that have high conflict but could support some or a lot of beaver, and those might be good source areas. But the capacity model itself is driven by a fuzzy inference system, and we want to take a closer look at those. And it's going to predict whether or not there can't be any dams or rare dams, occasional dams, frequent or pervasive densities. And so the way that works is there's an inference system. There's actually one that spits out well, how good is the vegetation? Is the vegetation suitable dam building material? And it looks at that both right next to the channel and then in an area up to 100 meters away from the edge of the water, because that's about as far as we find beaver going to use those. And this is the primary driver of the model. But then you can have what's the stream power, so discharge basically times slope at low flows. And we use that low flow stream power estimate to ask whether or not they can even build a dam. And so in these blues, these are areas that they can definitely build a dam. The water base flow is definitely low enough that they can do that. Versus these red are areas where they cannot build a dam. It's just too steep. And then we look at what are typical flood flows. So we use Q2, the 2-year recurrence interval flow, as a proxy for a typical flood, and whether or not dams are definitely going to persist in response to that flood, may occasionally breach or blow out, or they're definitely going to blow out in red. And we can also look at slope. Densities go down in really flat areas because they don't need to build as many dams to inundate the same area, and in really steep areas, then the slope, the upper limit on slope, even though it's included in stream power, and particularly in headwater reaches, that can limit whether or not they can build a dam because it's just it's too steep. And then we also have a drainage area sort of filter, which basically, when you get into really big rivers with really large stream powers, even at base flow with really low stream powers, the river is just too wide, too big for them to build a dam. And so how do I combine all of these to get this combined output? And that's really the challenge, and that's where the fuzzy inference systems come in. So this is that first one that I mentioned. And so we can take something like vegetation type, and we can look at that in the riparian area versus within 100 meters from the channel, and these are just going to be values between 0 and 4. Up here at 4, that would be preferred habitat. Down at 0 would be unsuitable habitat. So this would be things like aspen and willow. This would be things like bedrock or a road, and then we have everything in between. And depending on the number that you get, we can obviously have quite a bit of overlap. And then there's a rule system that says, well, if this or that, then produce none, occasional, healthy, etc. Well, where this the real meat of these models is in these what are called .FIS files, and it's really important that you understand first the rule table. And so I already showed you these input membership functions, which just define these classes. And in here you have a header in your .FIS file which says how many inputs are there. Well, in this case there's 2. How many outputs? There's 1. And then what are the methods by which this inference system works. And then you can go to the inputs. And so here's input 1, and that's riparian vegetation preference cover. So we can go back. That's this one. And input 2 is going to be adjacent vegetation. So there's input 2. And we can see how many membership functions. 1, 2, 3, 4, 5. Look at that. Unsuitable, barely suitable, moderately suitable, to preferred. So I can go back. Those are these categories coming across. And then I have the specification of triangular membership functions, or I can have trapezoidal membership functions. And so these actually in this picture are trapezoidal. A triangular would be one that just had a 1, 2, 3, right? And so what you can do is see that, so for unsuitable it's triangular, so the first vertice would have been 0. The second vertice also 0, and then the third would go on up to 1, and then there's this overlap with the next one. We'll see they overlap at 0 and 1, 0 and 1, and so this is the peak membership at 1, and then 2, and so 1 and 2 overlap here, 2 and 3, 2 and 3 overlap there, 3 and 4, 3 and 4 overlap there, and so you can see that these things are just described mathematically with these simple sets of numbers. And in the case of a triangular membership function, you have 3 vertices. The first one is where membership is 0. Second one is membership is 1. Third one is where membership is 0. And then in the trapezoidal, you have 4. And so this would be membership of 0, membership of 1, membership of 1, membership of 0. And those are just plotting out what those membership functions look like. So that's one part of the FIS, and the other part is the rule system. And so in the FIS it has a column for rule 1 and which input you're referring to, so membership function 1, 2, 3, 4, 5, and then a column for membership for the second input, and then which membership function, 1, 2, 3, 4, 5, and then a comma, and then you have the output membership functions and which one it corresponds to. And so in words, that's just like saying if the suitability of streamside vegetation is unsuitable and the suitability of upland riparian vegetation is unsuitable, then the output is none. Versus if I come down here, if the suitability of streamside vegetation is preferred and the upland is barely suitable, then we'll call it frequent. Versus if it's preferred, then we'll call it pervasive. And so these rules are just represented here in the inference system with those numbers. And then you have a weighting function, so you can apply higher weight to individual rules if you want. And that's really all there is to it. And so you can combine, we can have another inference system that combines that veg output with the stream powers, the base flow versus the floods. And this is maybe what the rule system looks like for that. And so here is an example where the vegetation output is none. It doesn't matter what the base flow or stream power is, the dam density is still none. Versus if I have an area, let's say, that has pervasive output based off the vegetation, they can build a dam at base flow, and 2-year floods, the dam persists, then the output itself is pervasive. Versus I can have a situation where that pervasive vegetation, to support pervasive dam densities, and they can build dams at base flows, but because it almost always blows out, the densities are limited. In this case, it's occasional. And so those are ways that I can combine these different inputs to get an output. And so here's an example of what this model looks like run for the Logan Blacksmith watershed. Again, the blues are the highest densities, the reds are lower. What this is suggesting here, this is a little zoom in showing the yellows are all individual beaver dams. These are the individual beaver dams. So there's about 625 dams shown here. It's actually closer to 1,100. I've gone back and resurveyed this. But you can compare, with these different colors, these different densities, what sort of electivity indexes we see, and we see higher electivity indices above 1 for these frequent and pervasive. And you can also take those dam density estimates and multiply them by segment length, and then you can come up with an actual number of dams that we could support in those areas. So finally, if I combine that network model underneath, I could have another fuzzy model, and this is what you're going to do in lab, where I can look at what is the suitability of or the likelihood that an area would be attractive to a cow, basically. And so this is going to be an occupancy model driven by vegetation, proximity to water sources, and slope. And so we can look at the outputs of a raster-based model and a network model right next to each other. Both of them can be driven by fuzzy inference systems, different fuzzy inference systems. Okay, so that's it for that segment. Next, I'm going to talk to you a little bit about some bioenergetics models.